thanks.
So you see the slides, right?
Yeah.
So today we conclude talking a little bit about unsupervised techniques. I will not survey all the possible unsupervised techniques, but I will concentrate on one specific kind of architecture that allows us then to go into the hands-on part, playing explicitly with an application which is anomaly detection. So the architecture I'm gonna discuss is the autoencoder, which is it's basically this kind of bottleneck structure that you see on the image in the slide. So you start from some input X that live in some n-dimensional space. What you do is that you compress it to some latent space, and then so you map it to some other k-dimensional space with some function f, and then that's called the encoding step. And then you go through a decoding step in which you go back to your initial Rn space, obtaining an image of X that you call X prime. And the idea is that a well-trained autoencoder should give an X prime which is very close to X. So in other words, you're trying to learn the identity function as a sequence of applying a function and its inverse. So why are you doing this? There are several applications you can have in mind. One is it's a compression algorithm. Effectively, this is like a principal component analysis, that except that it's not linear in nature, because with a network you can go beyond the linear assumption. So historically, this is the kind of architecture that is used to make your data smaller, retaining the essential information, and then just use this compressed data in outside. So in energy physics, you would imagine that this is a way, for instance, for you to pack the data in the front-end electronic of a detector when you want to ship it out. So you have an image, an example in the bottom of what an autoencoder can do. These are handwritten digits, part of the MNIST data set, which is a classic in machine learning. And you see in the bottom the kind of image that you reconstruct. You see that you're blurring a little bit the image. On the other hand, except for some pathological cases like I think that's a 5 that gets into a 9. There is a 4 that gets into a 9, but in the other case, it works pretty well. Now, cannot go on. Lost track of my mouse or some such. Okay. So, what an autoencoder could also be interesting for is for clustering purposes, because effectively what's happening is that when you start from some input and then you map it into this k-dimensional latent space, this mapping is a deterministic function. So things which are similar tend to be mapped into the very same point or nearby points. So for instance, this is an image that shows if you take the handwritten digits of the MNIST dataset and you process them through an autoencoder, the color coding there tells you where the different digits land. And you see that you start to have islands in this plane, which this is for an autoencoder with 2 dimensions, and these islands correspond to different digits. So in this sense, it's an unsupervised learning because your algorithm doesn't know anything about 1, 2, 3, and 4, but it manages to map them into different places. And then you could cut on this plane to isolate regions where most likely you will have a digit 2 or 3 or 4, whatever you want. So it works, it's a compression architecture that works well as a clustering algorithm. So how do you train an autoencoder? So it's similar to a supervised training, except that you don't have any more the labels, so you don't have a target. Or if, in other words, the target is the input per se. So you specify, as usual, the X data set, which is the input that you give to the network, and you use as a target X itself. And you're trying to minimize with some distance, the distance between X in input and X in output. And typically this distance could be an MSE loss. I mean, anything which could be like a regression kind of loss, but it could also be, people sometimes use cross entropy and so on. This is something like a minimal setup that you could consider to use, but then we will see that you can do even more sophisticated things. For instance, if you look at the literature now, there is a lot of talking about specific metrics that would measure the distance between jets that you could use as a loss in order to do this exercise. And then if you apply it to our problem, you could, for instance, say that you take some real data sample of jets, which to large extent are QCD jets. So in our example, you could select in our datasets the gluons and the quarks, and then you could train your autoencoder. And then once you have trained the autoencoder, you could apply the autoencoder to different kinds of jets. And so what you expect to see is the following. Since your compression and decompression algorithm is tuned on the events that belong to the training dataset, the network reaches some performance in this compression, decompression for that kind of event. If you present something that is new, anomalous, it's just different than what's in the training dataset, you're not guaranteed that the compression and decompression will work. So what happens is that in average, you would expect that the compression would be less effective, or in other words, your output would be more distance than the input than in a typical case. And a nice way, an obvious way of measuring this is just to measure the distance between input and output with the very same metric that you use for training, which is your loss. And in this image, in this histogram, you see, for instance, the distribution of the losses for the other kinds of jets, and you see that except for the top, in this specific case, you tend to have a shift, even for the top to some extent. You have a shift to the right that tells you that the tail is enriched with anomalies. And so you could imagine to use this to identify anomalous jets. Now, here I discuss something which you can, I mean, in the examples that we're gonna see, we are gonna just write down the encoder and decoder as plain dense neural networks. On the other hand, you could imagine to use the kind of complex applications that you use so far to define autoencoders. For instance, you can discuss, you can create a convolutional autoencoder that works with the jet images that we played so far. Now, the encoding part is easy because it's very similar to the kind of classifiers that we've been working so far. You will start with some convolutional layer, then you might have some max pooling and so on and so forth, until you reduce, basically you feature engineer some number that then you can inject into some dense layer, and then you end up in your bottleneck latent space. When you then want to decode this, you need to apply the opposite transformation. And the opposite transformation is for the max pooling is what's called an upsampling, which is again something you can do with zero padding, same padding, and so on. And you see the representation on the bottom. So you start with a 2x2 image, which is 1, 2, 3, and 4, and you expand it into a 4x4 image, padding it with zeros or padding it just repeating the number. This is what's called an upsampling. And in the top, you see a sketch on instead of what the conv transpose is doing, which is the, if you want, the opposite operation as the convolutional. And so you have all the ingredients to basically do the transpose operation of the convolutional and then basically expand from one-dimensional array to your image. And if you do so, there are these two papers that I linked in the top right that you can check. These people independently basically did the same thing. They started with jet images similar to those that we played with on Tuesday and did this encoding decoding. And then they looked at the loss of the distribution of the loss for the QCD, which is the gray distribution, overlaid to the kind of distribution they would get from boosted tops, which is very similar to what we're gonna do later, or even gluinos, which are like, in this case, this was R-parity violating gluinos that were decaying to 3 quarks, and you would get, like in the top, overlapping jets that would have some substructure. And so here, if you just ignore this information and you try to do your analysis on the whole data set, you will have some S over B, which typically is small. The idea is that if you cut on the loss at some point, you will basically enrich your sample of signal by enhancing the S over B. And the point is that why would you do so? If you are looking for tops, or if you are looking for gluinos of 400 GeV, you should never do this, because if you know what you're searching for, you want to tell your training algorithm, your training process and your algorithm, because there is a lot of information inside the specific signal hypothesis that you want to consider. But if you don't know what you're searching for, and you just know what you don't want to keep, so if you know your background, if you want, but you don't know your signal, then in that case, it's a different story. And this kind of approach would fit your use case. You should not expect as good performance as in a supervised application, because the supervised application is based on much more information than what enters in this case. On the other hand, you gain in generality, because once you train your algorithm once, you can use it to serve many scenarios. And particularly in situation where, as in the experiments of the HC, where you have computational constraints, for instance, a trigger level, having such an algorithm that in place could be an interesting thing to complement the physics program. And then this slide was just to tell you that you can even do recurrent autoencoders. And this is actually what's done in natural language processing, like Google Translate works this way. So you have one encoder that goes from a sentence written in English into the latent space, and then you have the decoder that turns that point of the latent space into the corresponding sentence in French. Okay. Now, if you take this idea and want to apply in physics, as I said, if you know what you're looking for, you run a supervised search. Supervised search is what you should be doing, because it's basically the best you can do, because it's the best way to use all the information that you have. The problem is that there is a sociological bias somehow at play here, because particularly in a machine like the LHC, where you cannot take all the events and you need to specify upfront what you want to select, you can only discover things that for which you wrote a trigger. And so it's your capability of discovering unexpected signal, somehow it's conditional to the fact that this unexpected signal was triggered accidentally by your set of triggers that you put together thinking about other stuff. So somehow, when you know what you're searching for, like the Higgs boson, it's that this is not a problem, because you exactly know all the expected decays, the purity of each one, you know where you want to invest your attention, and consequently where you want to put your bandwidth. When you don't know what you're searching for, it becomes a little bit of an hazard to rely on trigger by accident. There are physics cases where this is not the case. For instance, you could say, okay, whatever I can make at the LHC, I can make it plus jets. So I want to trigger on the jet, that is recording against the whatever object. I sacrifice the bulk of the signal production, which doesn't come with jets, and I only concentrate to the alpha strong square suppressed associated jet production. You could do that. We do that. Of course, you're losing a lot of statistics. And so you need much, much more luminosity to probe that signal, simply because the effective cross-section that you're probing is the production cross-section of that object multiplied by the reducing factor. This is due to the fact that you ask typically for a jet of several hundred JeVs to be there. Okay, so a more like theory agnostic way of dealing with this problem might be to have, on top of the usual physics program that we have in place, something that relies on standard model background vetoes. And these vetoes could be defined using the autoencoders. There is a problem that so the way this would work, then we go to the problem, is that you would basically have trained some algorithm, and then online you would just compute the loss, and you would cut on the loss. The problem is that the loss effectively is a metric, is a distance of metric between your input and your output. And the fact that you're cutting on the loss means that this metric somehow comes from some training. So there is a little bit of, there's a lot of arbitrarity here. And in particular, this is what in statistics is defined like a single hypothesis problem, where you don't specify the alternative hypothesis. And so you cannot do an hypothesis test, which is what we typically do to assess the presence of a signal. And so this is an ill-posed question. And so you cannot talk about optimality. There is no way you can train an algorithm of this kind, which is universally effective in finding any kind of signal you might have. And so, again, there is some luck that has to intervene, so you're not getting rid of that. But it is a complementary way to look at your data. So it's something that certainly doesn't hurt to have. You should just not expect that doing this, on the other hand, is sufficient. So now, what's the tricky thing? The tricky thing is that the LHC is a terrible machine if you don't know what you're looking for. This is something maybe it's not even stressed enough. The LHC is a fantastic discovery machine to discover something you expect. The reason being that it's basically money. So we produce 40 million events per second, collision events per second, but we only store 1,000 events per second. So to go from 40 million to a million to 1,000, you need to operate a very strong selection in your trigger. This is opposed to, for instance, LEP, where LEP is the other way around. You basically see, as soon as you see something interesting, you take the event, and basically the trigger efficiency was 99%. Here, it's way, way smaller. And so you need to, there is a strong sociological bias in the way the menu is put in. And it really depends on what you're searching for, dictates where you put your trigger. And then there is a lot of sociology happening, big collaborations. For instance, if you look at the CMS menu, you will see that for reasons that not everyone agree on, the tau trigger has a huge bandwidth, because there was a time when you wanted to score the Higgs in tau. Now that it's done, nobody understands why that trigger is so. We can give explanations of that, but are not very scientific. But in any case, there is a question.
Yeah, Kelly.
Yes. Can we perform this unsupervised algorithm fast enough for matching all the data from a detector like
Yeah, this is where I was getting. So I'll show you in the next slides an application that would certainly fit the high-level trigger, because I don't know if I have the numbers now. So the high-level trigger typically is an application that runs into a computer farm, where you have an order of 100 milliseconds to take a decision. The inference of a trigger of an autoencoder of the kind that we're discussing is within this time scale. So you can certainly do it. And even more, for other reasons, the experiments are only keeping themselves with GPUs in these clusters. So I see no problem there. It's really a solved problem. Level one, it's a little bit more complicated because level one has it's basically running on custom electronics and in particular on FPGA cards where there is no CPU. So this data, basically what you're running is a logic circuit and use the FPGA just as an emulator of the circuit. It's FPGA, you can look it as a universal logic circuit emulator. And so you need to program your FPGA to do what you want. And this is actually one of the reasons that motivated us to basically create a library to do this. Because as a use case, it's a little bit unique in the sense that a lot of other people have needs of to do fast inference for deep learning applications, but their time scale is more like high level trigger, like it's like 100 milliseconds. Like consider like a self-driving car, the reaction time that you want the car to have is at the order of hundreds of milliseconds. You need the car to react on a microsecond. Instead, a level one trigger at the LHC has to react within order of a microsecond. So you need to speed up your inference to the level of a microsecond. There are a lot of techniques to do this, and in particular, I removed those slides because I thought they were not very interesting to you, but okay, maybe we can go there and later in the discussion sections for those that we join. But we put together a library which is called HLS4ML that does exactly this. So you come out with a model and then HLS4ML does the translation to a logic circuit such that you can put it. And you can certainly speed up level one trigger to like the one that we're gonna play with to make it run, let's say within, let's say 100 nanoseconds. So well within the limits.
Nice.
And
And can you
actually,
imagine
this is
also hardware, new hardware for better performing these machine learning algorithms on new detectors? Would
yeah, the problem there, I mean, the advantage of an FPGA is that it's universal. Now, if you want to use like custom chips, I mentioned the IPU yesterday, then you need to, it's certainly possible at a high level trigger because typically vendors have in mind HPC, so hyper performing computing setups, so supercomputers kind of situation, where the main player is a CPU, an ordinary core, and then there is an accelerator device, which could be a CPU, GPU, it could be also an FPGA, but it could also be this exotic architectures. And typically this comes with a port with a, this is called the, it's basically you can just connect it to your cluster and that's it. While at level one, there is not such a thing. You have optic fibers with data that are just coming in from the detector. And so you need to somehow create an interface in which you could take this chip and actually plug it in there. For instance, at some point we consider the TPU of Google. The problem is that they don't sell it. So, and even the IPU, we're talking to GraphCore, but they're not super sure that it would fit. So at this moment, the best we can do is to come out with this, basically to program an FPGA. On the longer term, you could imagine that we could come out with a custom programmable chip.
Thank you.
Now, so this is a stupid example that we studied, this was a couple of years ago, to present this concept. So because there was a lot of talking about this unsupervised techniques, but nobody was pointing it out that you need to do this in the trigger, otherwise the event might be lost forever. And so we took a very simple example, like single lepton trigger, and we showed that okay, we have a set of high-level features that are listed there that we use to characterize these events. And these high-level features were chosen in order to be able to separate the different processes that would enter, so W production, Z production, TT bar, and KCD. And these are the features of the distribution of these features. And then what we did is that we had 21 of them, and then we did encoding, decoding, and so we compressed these 21 features to a four-dimensional space. And now we use this autoencoder on a set of signals, which are not crazy signals after all, like leptoquarks, scalars that go to multileptons, light Higgs that go to tau tau for the neutral one, tau nu for the charged one. So these are final states which are extremely tricky at the LHC the moment the resonance is produced as a mass which is lower than 100 GeV. It looks like a paradox, but it is what it is. Like if you want to look for a leptoquark of 90, 80 GeV that goes to taus and b's, if you look at the latest result that we have on this thing, because of the trigger, it's something like 10 years old. It's basically something we searched for at the very, very beginning. But then at the moment the LHC started to operate very, very well, we had to increase the thresholds of the trigger because we could not write those events anymore. And so as of today, on a leptoquark, you will have like a 10% efficiency, which means that effectively you need 10 times more luminosity to make a discovery because you don't have a trigger in place. And so the idea was to see if we could put something like the idea is not to use it yet for discovery, but the idea would be something like this. Can we have an algorithm like this that would select the 1 in a million events, the super weird ones, and create a catalog of a few thousand events per year that you can just store, and then people can look at offline. Like my idea was to publish these events, to just put out the events in electronic format and let everyone look at them. And then people might come with ideas of what these events might be. First, finding events which are alike in this data set, and then what this could be, and then this could trigger ideas on new models, and then we would put dedicated triggers to do the supervised search in the next run. So this was a little bit the idea behind. And this was just to demonstrate that if you put yourself a cut, so the cut that you see in the purple line there is chosen with the idea that you would select something like 1,000 events a month. 1,000 events a month, this means something you can still look one by eye. Okay. And so in order to give you a sense of, on the other hand, the pros and the cons, so okay, this is just to tell you that, of course, the moment you have a signal specified, you can run a classifier. And these are the kind of classification you would obtain on the various models. So this is the interesting plot. So this shows you the pros and the cons, in the sense that the thing that I was saying before, the narrow, the thick line are the autoencoder, and the thin one are the supervisor classifier, and the color coding means a given model. So what you see is that, for instance, at the point where we cut, you have a drop of performance, which is almost an order of magnitude, and more than an order of magnitude for, no, let's say it's at most an order of magnitude, but comparable to an order of magnitude. So this is to tell you, again, that if you really know what you're looking for, there is really no point in doing this. On the other hand, the thin lines there, the supervised, each line is an algorithm that was trained for a given background and a given signal. So the red algorithm would miserably fail on the green, on the blue, and on the black signal. Okay? So that algorithm works very well for a 4-lepton resonance. And even changing the mass of the resonance, you must see a drop of performance. Instead, the thick lines is the very same algorithm applied to different final states. So it's one algorithm that serves all the scenarios. It doesn't serve the scenarios as well as a supervised classifier, but it does a good job. So the target rate was 50 events per day. So it was 3,500 a month. So this gives you a little bit the idea, okay? We're not trying to send everyone home and have a AI operated CMS or Atlas. The idea is to have something else that would complement the things we're doing. What we're doing is good. It's a way that can discover new physics, and we know that because we already discovered particles this way. If we know what, make an hypothesis, we write a trigger that would select the events generated by this hypothesis. We select those events, we study them, and then if there is something, we discover it. But in order to go beyond the assumption we made at the beginning, this could be like a nice insurance policy, let's say. Now, I want to show you something else, which is still an autoencoder, but is more, let's say, fancy and typically works better. And it's called a variational encoder. So the idea is the same. It's that you start from some space, you compress it to some latent space, and then you go back. Except that now, when you compress to the latent space, you're not mapping your input point to one point, but to a distribution. If you want the probability distribution of where this point would land in the latent space. And the fact that you can account for a distribution is what it means, make it variational. In particular, this is a fantastic application to have a generator. So you could basically train an algorithm to learn a given data set, but since you have some probability density function that in the latent space, you could sample from this probability density function and create new instances of your data set. And this would be an alternative to, for instance, generative adversarial networks, if you heard about those. So how does it work? In general, it works that the encoder is learning the distribution of, in the latent space Z, given the X. And your decoder is learning the opposite. It's learning the probability of X given Z. If you know the prior of Z, you can basically use Bayes' theorem to write the probability of X, so to learn the distribution in a supervised way for your input, as the product of the decoder times the prior. And now you don't know the prior, but there is this trick that you can do, is that if you write your loss function as the reconstruction loss that we said before, so some metric of input minus output, and you sum what is called a Kullabach-Kleiber divergence between what? Between the distributions of, sorry, I didn't say that. So you structure the network in such a way that, let's say that you have a bidimensional latent space. So you want to land in a plane. Your inner layer is not two neurons, but it's two pairs of neurons. The first pair of neurons is learning the mean value of the distribution, and the other pair of neurons learning the variance, the log variance, the standard deviation, whatever you want. But from these quantities, then you can reconstruct the prior, the probability density function, and in particular, you do so forcing the prior, forcing distribution to be Gaussian. And how do you do so? Penalizing your training if the distribution is not Gaussian. How do you penalize it? You put a metric which measures the distance between the function, the distribution of your mu and the sigma, and a given Gaussian that you choose, which has sigma 0 and mu 0 and sigma 1. So what you're basically doing is that you're putting a penalty in your loss such that if you deviate from the prior that you have chosen, the loss gets penalized, and in your stochastic gradient descent, the minimum will go somewhere else. So doing so, in one shot, you're accomplishing two tasks. On one hand, you want to be able to reconstruct the output from the latent space, and this is what the loss Rigo is doing. And on the other hand, you want to, you're training to force the prior to be Gaussian. Once you have done that, you can then start sampling from a Gaussian, and applying the decoder, you would get a generator. And also this works as a clustering algorithm as well. It has the same functionality as the things before, but you can also do this. Of course, it's not, for images, I have to say it doesn't work that well with respect to state-of-the-art, for instance, generative adversarial networks, but it is giving you the sense that you have a generator. Why is not working very well? Because people speculated that simply the Gaussian assumption is not appropriate for images. And so people came out with ideas on how you could basically modify and go beyond this Gaussian assumption. But why is people so keen about the Gaussian assumption? Because if you use a Gaussian assumption, the Kullabach-Leibler divergence, which is effectively its relative entropy, it's integral of px log of qx over px, you can write down analytically the way. And so, and particularly you can write down in a way which is differentiable, which means that when you're going to compute the gradients of your loss, so the gradient of your loss with respect to the parameter of your network, you can actually solve this problem analytically, which means that TensorFlow knows what to do. If you instead want to use some other function for which the Kullabach-Leibler divergence is not differentiable, then you run in trouble. Of course, you could say, okay, I don't want to use the Kullabach-Leibler divergence. I want to use some other metric of distance between PDFs, which is differentiable. Of course, you can. But this is what people did. And I'm not sure that, okay, you can if you find one. But if you find one, it's a nice paper to write. Okay. So, and in general, I thought I removed this slide. Now it's there, so let's discuss this. So in general, it is true that with images it doesn't work that well, but for instance, variational autoencoders work very well with sequences. So for instance, to generate sounds, people manage to generate sounds learning, for instance, music. Okay. And also with the other kind of sequential data, like for instance, it was done with chemistry applications. There are references there, you can check. You got the idea. As of today, I think that the frontier would be to start to have this Gaussian loss there, but to structure your problem in such a way that in between the Gaussian sampling and the decoder, you put something else in the middle that would morph your Gaussian into an arbitrary function. And if you opportunely choose this morphing function in such a way that itself it is differentiable, then you can basically reconstruct the case of a generic shape for your prior, preserving the differentiability condition. And this is what is called normalizing flows. So people now are discussing a lot encoding and decoding with Gaussian sampling and the normalizing flow to reshape the Gaussian into something which you would learn in the training process. So I wanted then to show you why one would do all of this. As a matter of fact, one does it because typically it works better. So if you take the very same problem as before, so you see that the encoder and the decoder architecture is the same. And then in the middle, what we did is that we put this variational part where we have still a 4-dimensional space, but now we have 2 arrays of 4 dimensions, the sigma and the mu. We use mu and sigma to sample from the Gaussian the z, and then we inject the z in the decoder. But then the name of the game is the same. Okay, you have 2 components in the loss. I didn't say the beta in front is an hyperparameter that you can tune in order to weight the different contributions appropriately. I mean, as you want. Remember, the 2 contributions do 2 different tasks. One is the reconstruction, the other one is the fixing the prior. And if you are targeting as an application a generation task or an anomaly detection task, you would use different betas. And then if we did exactly the same problem, and then I think I wanted to show you is that particularly at the region where we're cutting, you somehow recover some of the performance. Not everything, but sometimes you recover a lot. For instance, in the case of the blue, you have a big jump in between the autoencoder and the variational autoencoder. It's still not as good as the supervised, but it's a substantial recovery of performance. Okay. So these are some number of the fact that one could probe cross sections for these kind of processes that are, as of today, unexplored. And I wanted to give you the sense that somehow you are trying to reformulate your analysis towards a model independence, a signal model independence. So you don't want to, you would like to have an alternative strategy to data analysis at the LHC, which has less dependence on the BSM assumption. So you don't want to stick on a specific BSM scenario. You lose performance, you'll gain in generality. Now, it's not entirely true that doing this, you remove the model independence, because remember that you get a collision, but then you have to code this collision in some data format that you would use as input. So in my case, I took 21 features. If the features are not chosen, the chosen features are not adequate to discover that whatever signal is hiding in my data, even this model would fail. So this is to say that the technique itself is halfway through the autoencoder, through the model independence. But of course, there is still some residual model independence in the way you choose the features. A way to go around it would be to use, for instance, convolutional graphs or recurrent networks to go back to the raw data. But still, at some point, you have to make some choice. And the only way that comes to my mind to go around this problem would be to have many of them operating in parallel. So this is to conclude. So I showed you this architecture, which is particularly rich of potential application. You can see it as a compression algorithm, as a clustering algorithm, as an anomaly detection. And then when you use into its variational version, even as a generator. In general, it can also be a way to improve the robustness of your anomaly detection because of this probabilistic ingredient you add on top that somehow can account for systematics. And in my take is that, I mean, particularly considering at run 3, then the amount of statistics we will collect in run 3 will be marginal for the overall LHC plan before we go into the long shutdown for luminosity LHC. So it's really the time to do different things. And this could be one of the things we might want to try in order to see if we find some surprise. So this is the last slide. And before we go to the hands-on, maybe we can see if there are questions.
Yeah, go ahead. Is anybody?
There is one.
Yep, hello. A question for the version autoencoder as a gun. So the structure for a gun, you have usually a generator and discriminator.
It's not a gun. It's a generative model. It's not a gun.
Right, but so the version autoencoder will then be taking the part of the generator, if one would.
No. It's so. What is it? The generator would be the decoder that you would to generate. So you would train with encoding plus decoding, and then to generate, you will sample from Gaussians, and then you will inject in the decoder.
Okay.
But be careful though, because the math is a little bit different in the sense that does everyone knows what's a gun? Maybe let me show you something. So this is a paper that we wrote with a student from ETH, who is master thesis. where we discovered the top quark in the LHC data. We pretended we didn't know that the top quark was there. And we used something which is in the middle of what I showed you, the variational encoder, which is this thing here, and a gun, which is this thing here. You see my mouse?
Yes.
Yeah.
Okay, so as we just saw in the variational encoder, you start from X, you encode it to some E of X, and then from E of X, you go back to X as D of E of X, okay? The GAN is a different idea. So you have some true data set X that you put on a side. You start from Z, so you start from the green, from the latent space, and you use a generator to create G of Z in the same format of X. So for instance, let's say that X are your 100 by 100 jet images. You would start from, I don't know, 30 numbers, and then you would use some convolutional transpose architecture to turn your 30 numbers into the 100 by 100 pixels, okay? With only this part here, you will get just random noise and you will not learn much. But what you do is that you put a critic, a discriminator in particular, that has to make the difference between the real images and the images you generated. And so now you have two networks. This is what is called adversarial, that you train against each other. So the loss is the loss of the generator, if you want, loosely speaking, minus the loss of this guy. Then mathematically you do it in a different trick. But what you're trying to do, you're trying to do a min-max problem where so if you minimize the loss of this guy, your loss goes down. If you minimize the loss of the discriminator, your loss goes up. And you let this thing train until your discriminator gets so confused that it cannot tell the difference anymore between these two. This means that the generator became good enough to trick it. And so this means that your objects here are somehow not distinguishable to some extent from the original one. So you learned the probability. You learn X as a probability. You learn X from Z, okay? Instead, so you did something similar to what a decoder does. And then there are people that says that, so unlike the variational encoder, a GAN doesn't let you place a given real image in a point Z of your latent space. It doesn't have a decoder. So sometimes people, what they do is that they do what is called a bi-GAN, which has also these extra ingredients. So it's a GAN with the encoder. And that, I think, is even a more stable way of dealing with this problem. Because at this point, remember, you have two spaces. You have the space in which your data live, and you have the latent space. With the variational encoder, you go from the physical space to the latent space and back. While with the GAN, you go from the latent space to the physical space. With bi-GAN, you do the same thing that you can do with variational encoder. You go back and forth, but you preserve the strength of this variational, of this adversarial learning, so this concept of training in competition, which seems to give better results, at least for generators. But then the nice thing is that once you've done that, you can even use this as an anomaly detection. So even GANs can be used for anomaly detection, which is what we did in this paper. Okay, so in particular, we use the very same 4 examples that I just showed you. And we had, there was a plot at some point that was showing the comparison between the variational encoder that I showed you and this one, and this is better. And then we use this to discover the top quark. So what we did is that we trained assuming that, pretending that we didn't know that the top was in our data. In real data, we use the real CMS data. And we train it on W plus jets and Z plus jets and this kind of stuff. And then at some point we cut on the tail, and we would expect to see, this is the colorful histograms are the Monte Carlo, the red is the top. So we would expect to basically be selecting a few tens of events, and instead we have hundreds of them and distributed according to the red. Of course, in real life, what you would observe is that you have many, many more events than what you would have expected. So the first thing that you check is, do I have a problem in my detector? You would look at when the events were taken. if they were taken all at the same week, most likely you had some problem in the detector, for instance. And then once you decide that this is not a spurious thing, but it's a real thing, you would look at these events to try to understand what it is until some bright theorist like you comes out with the idea and say, oh, but you forgot that there could be another quark there, and then you simulate it and you get the red thing. So this would be a different way of proceeding towards the discovery, where the first step is not someone comes out with a BSM idea to be tested, but instead we find an anomaly in the data, and then we try to reconstruct the kind of BSM idea that would explain the data effect.
Okay. And so I have also a more generic question about the Bayesian optimization algorithm. So when you have a project or a model that you are building, at which point would you run the algorithm? So would you start firstly to try a little bit manually, and then when you think it's doing what it should do, and then you run it?
First, you would do it by hand. You would try a few things. When you think that you find something that sort of work, you would ask yourself, which are the degrees of freedom you would like to move? Yeah.
Okay.
It also depends a lot on how much computational power you have, of course.
Right. Right. So for the examples that we did during this week, how long would it take to run the the Bayesian algorithm over them?
Those are not super heavy. I think that on a single GPU, like on a gaming card, took a week. So if you have access to like a cluster of GPUs and more powerful GPUs, you can short this down to a few hours.
Okay, that's good.
But you need to have access to the multiple GPUs and have the libraries to do so. And so it's a little bit more.
Okay, thanks.
Other questions? No. Okay, so let's no. So we go. Why is it doing so? Okay. Collab. So I prepared two notebooks, and one is with a plain autoencoder, and we're gonna go quickly through it. So the initial stuff is the same, so there's not much to say. We take the data. We go back to the first day list of features. So the 16 features for jets that we had, that we played with the first day. I tried with convolution and stuff. I had troubles with Colab crashing because of RAM. So I decided that we played simple today, but you get everything. The new ingredient of today is something I didn't show you in the previous days. It's something that typically people would do. So I show you the code. It's what's called a standardization. So the idea is that we have our data, just these 16 features for 50,000 events. And I'm basically shifting and scaling such that the mean is 0 and the RMS is 1. And I put some printout for you to see. For instance, the 10th feature, which I don't even remember what it was. The 10th feature is whatever, we can print it out. But in any case, it has a mean of 0.09 and an RMS of 3 to 10 to the minus 3. And after you standardize, we choose this standard library, the mean is 0 and the RMS is 1. Why this is important is because this is equalizing the values of all the inputs such that when they go into, for instance, the MSC, they have the same importance. In general, this is something that one would like to do always. So something you could try is go back to the old exercises we've done and do this before. You should see that the results improves. There is one exception that I think yesterday did it. Yesterday I put a batch normalization at the very, very first thing I did in the network. It's another way of doing this, except that that would be done on the fly, where this is done in pre-processing stage. Then, unlike the other days, I now use the labels not as a target, but to split my data set into what I call standard jets, so quarks and gluons, and then in W, Z, and top. Now I put the W, the Z, and the top on a side, and I only concentrate on the 20,000 QCD jets that I have. Okay, and then as usual, I would separate this into. First, I separate it into learning and test, and then the learning is separated into training and validation. So at the end, this is the training data set, this is the validation data set, and then I have an extra testing data set that I can use, that I can put on a side. Okay, so this is the encoding and decoding, and it's pretty simple. So we start with a 16 nodes input. We go into a dense layer of 10, activated by yellow, choice. And then we go into 5-dimensional latent space, again activated by yellow. So here we are in the latent space now. And then we inject this into the decoder, which does the thing the other way around. So it has a dense at 10 and then the dense at 16, which we get out. Notice that I don't put the activation function in the output, or in other words, I put a linear activation function because I don't want to constrain the inputs in a specific range, because the input is centered at 0, and so it can go positive, it can go negative. And for instance, if I knew that the input was between 0 and 1, I might have used a sigmoid here. If I knew it was between -1 and 1, I could have used an hyperbolic tangent. But since I don't have a predefined range for the input, I don't apply a predefined range for the output, so no activation function is the best choice. And then I use MSC for training with Adam. You see it's very small model, 400 parameters. And then the rest is the same. The training instruction is slightly different because now you see that I have X train, but also the target is X train, because my target is my input. You must remember, we're trying to find the distance from the input. And then this goes, it's pretty quick. Literally stops at before the 100 epochs. And now what I do is that I go back to the other data sets and I apply the autoencoder to them and to the test QCD. And once I apply that, by end I recompute the MSC, so input minus output, and I get some distribution for the QCD. And then on top, I put the distribution from the other. And you see that it's not like super discriminating. It's also true that the training data set is pretty small. But you see, for instance, that if you cut like 40%, the background rejection is comparable to 40%. If your line was crossing here, you would basically have the same signal background efficiency. So you would have like tossing a coin. So for W's and Z's, we are slightly better than tossing a coin. But for top, you start to have some discrimination, okay? Then, of course, as I said, the model is pretty small and it's not, and the data set is small. So in real life, you would use way more data and try to get it better. Are there questions on this? Doesn't seem so. So this is the same thing, except that now I show you the variational encoder. The beginning is the same, so there's not much to say. So here it gets a little bit more complicated. So first of all, the sampling that I told you with the Gaussian generation, you have to code it yourself. I mean, there are infinite examples on the internet you can copy from, but this is what's happening. So I'm assuming that I'm reading in the mean value and the log of the variance, and I'm just doing the generation. And so what I do is that I generate numbers around 0 with RMS1, and then I scale by the mean and I multiply by the sigma. And then I also need a custom loss function. So this is an interesting thing in general. I need a custom loss function because it's not gonna be just the MSC term, which is pre-coded in Keras. I also need to add this KL term, which is this thing here. So the way this is done is that I start with my loss, which is MSC, you see, I do output true value minus predicted value square, and then I sum across the last index, which is the features. And then I add on top of it the KL term, which depends again on the log var and on the mu. Now, this is a little bit weird because I do so defining a new layer, and this is done in such a way that these things exist when I'm doing the computation. So it's a little bit TensorFlow technical, but so because of we coded it is, so basically coding this custom layer, we make sure that when the loss is computed, Keras knows what to do. And then the architecture, it's I didn't run this. So the architecture is similar. It's the same 10 layers with Elu, except that now you see that out of this intermediate layer, I create two outputs with the same dimensionality, which is latent dimension, which I set somewhere. Oh no, which is an input. I will set it later to 5 here. And then out of the z and the mu, I define this special layer, which returns the same objects, but allows me to do this trick in order to compute the loss. So it seems like nothing is happening here, but what is happening is that the KL term of the loss is computed. Then I sample objects out of this mu and log var using the sampling function we have above. Lambda layer is basically every time you want to make an mathematical operation on a layer, you define a lambda layer where you say what's the operation you want to do. In our case, it's the sampling. And then I put sorry, and this is the encoder. Then okay, I'm compiling it usual way, and I'm making the summary. Then from there, I have my decoder that has another layer of 10. So it's 5 to 10, and then 10 to the input dimension, which is 16. And then I compile the decoder. The variational autoencoder is the decoder applied to the argument number 2 of the encoder. The encoder returns 3 objects. It returns the mu, the log var, and the z. So when I say encoder 2, I'm selecting the z. And then I compile it, and you get a lot of printouts. So this is the encoder. So you see that it starts with 16 features, become 10, then 5 and 5, the two separate 5s. And then you have these special layers and the sampling. The other one starts from 5, the decoder goes to 10, goes to 16. And notice also that again here there is a linear activation function for the output as before. And the decoder, the autoencoder is encoder, decoder, and that's it. 516 parameters in total. It's slightly more than the previous one because now we have 2 latent vectors, so there are more weights. Then compiled and running, and it's the same as before. So, I wanted to look at the difference. Okay, the scale is different, so you don't learn much, but you see by eye that not really. He didn't pick up my latest comment. No, I didn't. So this is something weird which is happening, which is that, so here I'm doing the sum over the 16 quantities while I should be doing the average. So what is happening here is that since I'm not doing divided by the number of sorry, since I'm not dividing by the number of entries that enter in this sum, I'm making these objects an order of magnitude bigger than what it should be. So this is a mistake, which I fixed in the, but I think I forgot to commit it on GitHub. So what is happening is that if we go back to the slides, effectively and by mistake, not by intention, I am picking a bit, so I enhanced this guy by a factor 10, 16 actually. So in other words, I put a beta factor here, which is 1 over 16. And so I'm downgrading the importance of DKL, which in the specific example that we have at hand makes the results worse. So in real life, this is something with variational encoder you always would do. You would scan beta and you will look for the best performance function of beta on your benchmark signals. Okay, now this is the code that I wanted to run. Because here now I'm dividing by the number you see here I have a mean, and I was doing the, I was supposed to do the mean even on top. What's going on? So if I redo everything, maybe. Okay, so this is the thing I wanted to show you. So this is basically with beta 1. And already with beta 1, you see that the top gets a substantial discrimination now. It is not as good as we used to with the supervised. Remember, with supervised, we used to be here. So we are not on magnitude worse, but it's definitely better than what we have with a plain autoencoder, because the AUC for the top is 80%, while for the other one is 72. On the other hand, notice that this is not a universal statement, because particularly the W is basically the same, 59 versus 55. And Z is slightly better, 62 over 56. So this is to tell you that this is a practical demonstration of the fact that because you are dealing with a one-class problem, There is no optimal. Something that works for model number number one might not work for model number two. And this is a little bit of where the problem stands. The fact that you're learning a metric, but you don't know, you're learning the metric looking at the standard model. And nobody tells you that that metric will be optimal for the whatever signal might be hiding in your data. Okay. Question, yes. Comment?
Yeah.
Yeah.
Another question. So let's assume that that we have chosen our hyperparameters in a way that gives us the best result. And for the variational autoencoder, you have kind of to define the reconstruction laws. And let's say for the best parameters, our result isn't still very good, what we want. What would you change? Would you change the reconstruction laws, the function for it?
It depends really on the cases. So sometimes you would see, for instance, that the features that you're reconstructing are just badly reconstructed. In that case, you might ask yourself, did I use the right loss function? So is MSC a good choice? Did I use the right activation function? For instance, if your data are all positive and you are letting the values to be positive and negative, maybe the network is struggling understanding that. So you can help the network by putting a ReLU activation function on a subset of your outputs. So typically, these are the things that one will look at. Then eventually, when you convince yourself that everything is in order and there is no like logical flow, you would try maybe with more data and a bigger network to see what happens. And if you see that there is an improvement, at that point, you start to ask yourself, should I do an hyperparameter scan? For instance, one of the typical things you would check is the dimensionality of the bottleneck. If you're taking a dimensionality which is too small, then the network might struggle reconstructing the output. Then there is another thing you should always keep in mind, that the problem with anomaly detection, from a statistical point of view, anomaly detection doesn't make sense. As I said, it's a need post question. You are trying to optimize your network on task A, which is learn to reconstruct the data that I give you. And then you want to use that to basically look for something else, quote unquote, by difference. Now, the fact that if you have a new kind of object, your variational encoder would not be able to reconstruct it, and then you will have a big loss, is not necessarily the case, might not be the case. And so even the algorithm that you enforce to define the anomaly somehow might be subject of study, in the sense a lot of people are speculating. For instance, there is a paper, it's a very nice paper by DeepMind, for instance, that shows that when you present your variational encoder with something new, because since the variational encoder was not trained to deal with this kind of events, it struggles in doing the compression decompression. It stresses this stresses the KL term in the loss, which becomes particularly big. And you might not see this doing what I showed you, because as here I just use the reconstruction loss as the figure of merit for anomaly. Instead, they claim you should use the KL, the regularization term, which is the KL loss, as the anomaly. And they showed that doing so, they have a better anomaly detection. Other people say that you just basically trying to run some clustering application in the latent space, and based on that define a contour out of which you would call something an anomaly. So the fact that you cut on the recall loss is only one way of doing that. And again, this becomes extremely case specific, so there is no general solution. And again, it's a little bit of you're not walking on solid ground, because there is no natural way for you to be able to say that what you have is optimal. The only thing that you can show is that what you have is effective in discovering anomalies that you imagined. And now the generalization power of these, it's not something you can assess.
Mm-hmm. So, if I understand it right, the KL loss task is to force a Gaussian distribution in the latent space, right? So,
Yeah.
so, so let's say, so the thing is, we have kind of two loss functions, the reconstruction loss and the KL loss, and the KL loss is defined, right, because of this Gaussian distribution, and you can play it. The only thing that would change would be the reconstruction loss, and let's say we have like a case, depending on the weight that you choose for your KL loss, you might get like a nice Gaussian distribution in your latent space, but on the other hand, your reconstruction becomes much worse, or vice versa. When you weighted it less, your reconstruction loss becomes better, but your distributions doesn't look so nice Gaussian. Um, so because the only thing that would be able to change would be the reconstruction loss, right? If you want somehow to modify it, would it be like because of a bad choice of your
No,
reconstruction loss?
you could even do the thing that I said before. I mean, you could use normalizing flows. So basically, you could define your prior as a function of a Gaussian, and you could learn that function. So it's not changing the loss, but it's somehow including in your network trainable parameters that allow you to go beyond the Gaussian assumption. I think that this is the thing that I would do in that case. So normalizing flows can do interesting things like, so for instance, if you look at this, like that. So you can start from something which is a Gaussian, and you can create an arbitrary function with it. And these things, these functions that you put in the middle are differentiable functions whose parameter you can learn in the training. So you would still have a Gaussian, and you will still have a KL term, which is the Gaussian KL term. And now your RICO loss would also depend on these extra parameters of these transformations that you are applying. And somehow you could change the numerical value of your RICO loss using this kind of things in such a way that you are incorporating the information of the fact that you want to use a prior which is not Gaussian. And you can do, people are like using these things to learn gauge distributions, gauge symmetries, and it's like start sampling from a, there are papers, for instance, they use a lot of this they propose this as a tool to create configurations for lattice QCT. Like, you know, that you like to generate points according to some group symmetry, and then you start with something generic, and then you enforce the symmetry using this kind of functions. I think this is the most powerful thing that you could do in order to somehow have a continuous spectrum of possibilities and not being forced to stick to the Gaussian. Because as you said, the Gaussian, there's not much you can do there, right?
Yeah.
But there are other people that suggested other things. For instance, the fact that your Gaussian, so basically the KL that you write is the KL distance between a generic Gaussian and a Gaussian center at zero in RMS1. So people say already the fact that the RMS is not one and the mean is not zero is a measurement of anomaly. And so you could just imagine that in the latent space, you just take a sphere, and everything outside that sphere, which is, I don't know, 5 sigma sphere, and everything outside that sphere, everything which lands outside the sphere, you just drop it, and you call it an anomaly if you want. So After all, this is a construction. It doesn't come necessarily with one specific definition of anomaly, and then you can optimize also the definition of anomaly in the stage.
Okay, thanks. It was very helpful.
We still have 5 minutes if there are questions.
Any question now? Or I remind you that we have the discussion section at 6:30. So you might also think about it a bit.
Fabio, today it's at 6.
6, sorry, 6. Sorry.
Yeah.
Thank you. So you have only 1 hour to think about it.
Okay, so I also need to rush and get the girls before coming home. So it might be slightly late, hopefully.
Maurizio, let us thank you so much. We'll do it also again. And in the meantime, thanks so much for your lectures.
You're welcome.
Very, very useful. Thanks.
I hope it was. I hope you enjoyed it. And as I said, if you have questions and you cannot participate later, just drop it on Slack. Okay.
You're having a virtual standing ovation here, so everyone's thanking. Whatever. What we do what we can, right?
Yeah.
Okay.
Okay.
Very good.
We like that.
Okay, talk to you all in an hour, guys. Thank you very much.
Bye-bye.
Bye.